afternoon, everyone. First, let me introduce myself. My name is William Mendieta. I'm a PhD student at University College Dublin, working under the supervision of Dr. Damian Flynn. Today, I would like to present the recent findings of our work, which is focused on investigating Type 5 hydrostatic transmission-based wind turbines. The title of my presentation today is Evaluation of Type 5 Synchronous Wind Power Plants in Power Systems with High Non-Synchronous Renewable Shares. This is the outline of my presentation, which is divided into 5 sections. First, I will introduce the motivation for this research, and I will provide some background information on the main characteristics of hydrostatic wind turbines. After this, I will discuss the model and the associated control system for a single hydrostatic wind turbine. Then I will present some results regarding the steady-state characteristics and the dynamic response of a single hydrostatic wind turbine. Next, I will present the approach used to model a hydrostatic transmission wind farm, and I will discuss its stability impacts on a power system. And finally, I will present the main conclusions of this work. So with respect to the motivation, we have that the forecast for the coming years shows a further acceleration in the integration of new wind projects. And for many countries, wind energy will represent the most widely used form of renewable energy sources. So when operating a power system with a large share of wind generation, the system's synchronous inertia and grid strength is typically reduced. So power systems have traditionally relied on synchronous generators to maintain system strength and physical inertia. So as a result, Type 5 wind turbines with grid-forming characteristics and synchronous attributes may become attractive for power systems with a high share of renewable energy sources. Hydrostatic wind turbines use a hydrostatic transmission to transmit power from the turbine rotor to a directly grid-connected synchronous generator, which provides several advantages such as voltage support, large fault currents, a natural inertial response, among others. So in addition, we can include a hydraulic accumulator so to the hydrostatic transmission in order to compensate for wind speed variations and also for grid disturbances. And finally, since the Type 5 hydrostatic wind turbine interfaces with the grid through a synchronous generator, its dynamic behavior is similar to that of a conventional generator. So some background information, some comparisons between variable speed wind turbines versus Type 5 hydrostatic wind turbines. We have that a variable speed wind turbine uses a mechanical gearbox to transmit power from the turbine rotor to the electrical generator. So in contrast, in a hydrostatic wind turbine, the turbine rotor drives a hydraulic pump, so which converts the mechanical power into hydraulic power in the form of a pressurized fluid. This fluid is then fed to the hydraulic motor, which converts the hydraulic power back into mechanical power to drive a synchronous generator. Variable speed wind turbines are connected to the grid via a partial or full power converter. On the other hand, since the hydrostatic transmission provides a continuously variable transmission, a synchronous generator can be connected without using a power converter to match the grid frequency. Some drawbacks regarding the hydrostatic wind turbine, we have that the hydrostatic transmission has a lower efficiency compared to a mechanical gearbox, especially a par load operation due to hydromechanical and volumetric losses. So we have that, for example, the efficiency of the hydraulic pump, it's about 87%, and the efficiency of the hydraulic motor is about 82%. So that gives us around a total efficiency of the hydrostatic transmission of about 78%. Nevertheless, apart from the synchronous attributes of hydrostatic wind turbines, they do offer various advantages over variable speed wind turbines that may compensate for their low efficiency, such as, for example, improved system reliability, flexibility. For example, we can place the synchronous generator either in the nacelle or at the base of the tower, and also these type of turbines, they have lower maintenance costs because we remove the gearbox and the power converter, and also, as I mentioned before, because we have the ability to move the generator to the ground level, so making also the tower structure lighter and cheaper. Variable speed wind turbines are unable to produce a natural inertial response since they are connected to the grid through a power converter. They can, however, provide a fast frequency response by adding additional control loops to their control system. So in contrast, a hydrostatic wind turbine will naturally provide an inertial response, which can also be improved by controlling the accumulator, and also we can add some fast frequency response control loops. Yeah. So the Type 5 hydrostatic wind turbine model integrates relationships between mechanical, hydraulic, and electrical systems. For example, the turbine rotor, the actuator, the hydrostatic transmission, the hydraulic accumulator, and the synchronous generator. So the model that we have includes 38 differential algebraic equations and has 6 control loops. Here, the pitch control operates in a similar way than in a variable speed wind turbine, so it regulates the aerodynamic input power for operation above rated wind speed conditions. The maximum power point tracking control regulates the motor volumetric displacement in order to adjust the turbine rotor speed for maximum power extraction. The fast frequency response control adjusts the motor volumetric displacement in order to adjust the fluid pressure in the hydrostatic transmission to transfer rotational energy from the turbine rotor to support the inertial response of the synchronous generator. The accumulator can be discharged or charged in order to support the inertial response of the synchronous generator during low frequency events. And also the accumulator can be charged and discharged to smooth the output power during turbulent wind speed conditions. Finally, the AVR operates in a similar way than in a conventional synchronous machine. So the studied hydrostatic wind turbine corresponds to a modified version of the NREL 5 megawatts variable speed wind turbine, in which the gearbox and power converter has been replaced by a hydrostatic transmission. So here, the wind speed is increased from 0 to its maximum operating limit to determine the steady state characteristics of this Type 5 wind turbine. The figure on the left shows the efficiency of the hydraulic components and the hydrostatic transmission over the operating wind speed range of this wind turbine, and the figure on the right shows the generated active and reactive power. The hydrostatic transmission has an efficiency of about 78% at rated wind speed conditions, resulting in a rated electrical power approximately of 4 megawatts. Since Type 5 hydrostatic wind turbines behave as a voltage sources in power systems, we can see also that the active and reactive power are coupled. Um, In order to investigate the dynamic response of a hydrostatic wind turbine, the following case studies are proposed. So first, the first case is the hydrostatic wind turbine is exposed to a turbulent wind speed profile in order to resemble real-life conditions. For the second case, we have a 10% load increase at 2 seconds to evaluate the frequency response characteristic of the hydrostatic wind turbine. And the third case, we have a three-phase bolt fault at bus 1 to evaluate its fault right-through characteristics. So the studies are conducted using a single hydrostatic wind turbine that generates 4 megawatts at a rated wind speed of 11.4 meters per second, and which is connected to a 7-bus 3-generator electricity network, as shown here in the figure in the bottom. So again, the hydrostatic wind turbine reaches nominal conditions at a wind speed of 11.4 meters per second. So here we have that the figure on the left shows the turbulent wind speed profile, which transitions between regions 2 and 3. And the figure on the right compares the output power generated by a standard hydrostatic wind turbine against a hydrostatic wind turbine equipped with an accumulator. So we can see, it can be observed that the accumulator acts as a low-pass filter, helping to noticeably smooth the output power of this wind turbine. So we are showing here some internal variables which are a critical factor for deciding the parameters for the control system. So the figure on the left compares the fluid pressure, the fluid within the hydrostatic transmission, between a hydrostatic wind turbine and a hydrostatic wind turbine equipped with an accumulator. So again, by looking at this figure, we can see that the presence of the accumulator impacts the pressure dynamics, making it smoother. The figure on the right shows the accumulator state of charge. The accumulator here is charged and discharged according to the variability of the wind speed. However, the control system avoids the accumulator reaching its operational limits in order to continuously enable the output power smoothing while keeping the capability to provide a response for frequency disturbances, as we will see in just a moment. So now the power system is subject to a sudden 10% load increase after 2 seconds, assuming that the wind power contributes to a 25% power share. So the frequency response of the hydrostatic wind turbine is evaluated based on the following frequency control strategies. The base case corresponds to a variable speed wind turbine without frequency controls. The second case, the variable speed wind turbine is replaced by a hydrostatic wind turbine, and thus the response corresponds to that of the inertial response of the synchronous generator alone of the hydrostatic wind turbine. For the next control strategy, the accumulator is discharged in order to support the inertial response. Then a fast frequency response control loop is added to extract rotational energy from the turbine rotor and also to support the inertial response. And finally, in the last case, the accumulator and the fast frequency response are enabled to support the inertial response of the hydrostatic wind turbine. So the figure on the left shows the power injected by the hydrostatic wind turbine during the frequency event. So as a result of the inertial response of its synchronous generator, plus the extra power obtained from the accumulator and the extracted power through the fast frequency response control loop. So it can be observed that the application of the fast frequency response leads to a larger energy recovery period. The figure on the right shows the frequency traces for the different cases. So for the base case, the variable speed wind turbines ignores the frequency disturbance, leading to a larger rock-off and lower frequency nadir. And then the frequency response is improved in all cases, but activating the frequency controls due to the additional power injection, which improves both the rock-off and the frequency nadir. Uh, it can be observed that the best result is obtained when we activate the frequency response and the fast frequency response. Sorry, when we activate the accumulator response and the fast frequency response at the same time. Again, some internal variables. Here we have the hydrostatic pressure within the hydrostatic transmission and the turbine rotor speed. So the figure on the left shows the pressure on the hydrostatic transmission. So in cases of inertia only and inertia plus accumulator, it can be observed that the pressure is only slightly affected since the motor volumetric displacement is not adjusted by the control system. So in contrast, when the fast frequency controls are activated, the pressure changes noticeably since the control system adjusts the motor displacement to extract power from the turbine rotor. The figure on the right shows the turbine rotor speed, which only changes when the fast frequency response controls are activated, showing that the rotational energy is being transferred from the turbine rotor. Uh, so now, as a test for illustrative purposes, so we are applying a three-phase bolt fault at the terminals of the hydrostatic transmission. So the figure on the left shows the zero voltage profile during the fault, which is cleared after 150 milliseconds, while the figure on the right shows the excitation voltage, which is automatically increased by the IVR as in a conventional synchronous machine. Um, Now, with respect to the power and the torque, we see that the figure on the left shows the active and reactive power contribution by the hydrostatic wind turbine during the fault. We can see that the active power falls to zero, while the reactive powers immediately increase as a result of the operation of the AVR. So once the fault is clear, the power returns to the previous steady state conditions. The figure on the right shows the electrical and mechanical torques. Again, given that the displacement of the hydraulic motor is not adjusted during the fault, so the mechanical torque is only slightly varied, while the electrical torque varies noticeably. Uh, so, in order to consider the stability effects of a large share of hydrostatic wind turbines, this figure, the figure on the right, shows an arrangement of a 60 megawatts hydrostatic wind farm, which is connected to the IEEE 14 bus test system. So in order to study the basic principles, a simple approach for the wind farm has been adopted, which does not consider wind direction, wake effects, and wind farm spacing. So here, a three-phase bolt fault is applied at the low voltage side of the collector transformer after 6 seconds to evaluate the behavior of the hydrostatic wind turbines within the plant and the potential of the accumulators in mitigating oscillations. So these figures compare the operation of the Type 5 wind turbine power plants exposed to wind speed ramps and during a fault event that occurs at 6 seconds. So frequency and power measurements are taken at the delta site of the corresponding transformers for each string. So the figure on the left shows that during the wind speed ramp, the system frequency remains close to nominal value with minor fluctuations primarily governed by the larger power system. So in the transitions from region 2 and 3 to, sorry, from region 2 to 3, the activation of pitch control after the maximum power point tracking mode rapidly adjust the pump torque to prevent exceeding turbine rotor nominal speed, so causing a fluid pressure transient and leading to a larger frequency peak. On the other hand, in the transition from region 3 to 2, the maximum power point tracking control mode regulates the motor displacement to mitigate fluid pressure transients, so resulting in a reduced frequency peak and a smoother frequency response. So the frequency on the right shows that during the fall event, severe frequency oscillations occur. So along with inner plant oscillations caused by the off-phase angle difference between the synchronous generators in the strings, which can jeopardize the grid stability and also lead to operational risks such as polyslip and potential damage of the generators if not effectively mitigated. So using an accumulator in each hydrostatic wind turbines offers a solution to mitigate oscillations in Type 5 wind power plants. So by regulating the hydraulic fluid during the frequency disturbances, it not only reduces the power fluctuations from individual turbines, but also may prevent pole slipping and associated damage with the turbines and generators. So in the figure on the left, the frequency response of the hydrostatic wind turbine number one of in string one, so which be the one here marked in this green rectangle, um, is studied. So first we study this with and without an accumulator. So it's observed that the accumulator effectively counteracts the frequency oscillations, so reducing the likelihood of generator overspeeding and also a loss of synchronism. So similarly, the frequency on the right shows the impact of the accumulator on reducing the power oscillations in string 1. Again, it can be observed that the accumulator rapidly absorbs and releases energy, allowing to effectively reducing power fluctuations. Finally, the capacity of the hydrostatic wind farm is now increased to 200 megawatts by adding 7 additional strings to the existing wind farm, such that the combined wind farm output of the wind farms can reach 70% of the demand. So then we apply a sudden 10% load increase in order to assess the impact on the system frequency response. So the figure on the left shows the cases when we have 100% synchronous generators. Then we replace this by the 70% of the synchronous generators is replaced by variable speed wind turbines. And then we replace these variable speed wind turbines with hydrostatic wind turbines. So it can be observed that in that case, we have a better response only with the synchronous generators, and with the rest of the cases, because we are losing some inertia, so the frequency nadir is lower for the two cases. The figure on the right, we activate the frequency controls for the hydrostatic wind turbines. So we can see that the frequency response is improved. For the case of the hydrostatic wind turbine, the inertial response of the hydrostatic wind turbine plus the accumulator, but still is not as good as with only synchronous generators. But then when we also activate the fast frequency response of the hydrostatic wind turbines, we can see that the frequency response has been improved. Some conclusions of our work. So hydrostatic wind turbines have lower efficiency compared to existing variable speed wind turbines due to hydromechanical and volumetric losses. An accumulator helps to smooth power output and compensate for wind speed variations and grid disturbances. Hydrostatic wind turbines enhance frequency response by combining the inertial response of the synchronous generator with the stored energy that can be the energy from the hydraulic accumulator. And also we saw that the integration of additional frequency controls improves the frequency response. Now, finally, we have this Type 5 hydrostatic wind turbine with the ability to provide similar characteristics to conventional